share the screen. So yeah, thank you everybody for coming along to Knots IoT. Before we start, and I did mention this to a few people who'd arrived earlier, we have a code of conduct in place. There's a lot of words on there, but it just boils down to just be nice to people. And if you feel as though someone's been unpleasant or breaking the code of conduct in any way, then by all means send myself a private message in the Zoom chat here, and we'll deal with that swiftly. We do take this really seriously, so just be nice to each other and enjoy the evening, essentially. We'd normally at this point be thanking Rebel recruiters in Nottingham, and hopefully in the not too distant future we'll get back to going to in-person events. But while we're virtual, they're not paying for our food or the seats we're sitting on. So my company there, PJG Creations, I've just put that in there because I'm doing all the work organising, so I think we could put that in there. But the Zoom license we're using, Tech Nottingham very kindly sponsor that, and I'll briefly talk about them. In fact, maybe Louise or Anna want to actually talk about Tech Nottingham on the next slide when I come to it. You're more than welcome. We've also got JetBrains. They're sponsoring us a 12-month license to any one of their products. If you don't know what JetBrains do, they make developer tools for developers. So we've already spoken about some of these: IntelliJ and ReSharper and WebStorm, PHP Storm, and things like that. And also, when we go back to in-person events, stickers will, I'm sure, make us some more stickers we can give you. We've got some here, but we don't have any sponsorship to start sending them out to people, sadly. So when we go back to in-person, you can have some more stickers. So just here. So did Anna or Louise, did you want to say a bit about Tech Nottingham as you're here?
Go on then. I just want to do a quick plug, if that's all right, for the Women in Tech workshop that we've got coming up. So it's a 10-week career coaching workshop. It's heavily subsidised for our lovely sponsor. So thank you to them. So if anyone on the call, like if they would just share it round, actually, because it is really good, eligible for women, non-binary and gender minorities, and I'll post the link in the chat. Thanks, Pete. I think Louise might shout out for Tech Nottingham, actually. I think we've got the next event.
Yep. So Tech Nottingham, biggest meetup in Nottingham, wide variety of topics, and currently available worldwide because, pandemic. So it takes place second Monday of every month. So the next one's the 12th of June. And let's test my memory now. It is Sophie Weston talking about blameless postmortems.
And you mean 12th of July, of course.
I did. That's exactly what I meant.
Don't worry, I did that.
I know how calendars work.
For this meetup, I was advertising this in one tweet to happen in July, and I'm sure Mike saw that and went, not sure what I'm speaking about or when I'm doing it now.
I just can't believe that we're almost halfway through the year already. That's what it is.
Yeah, geez. Solstice soon, in fact. So yeah, thank you so much to Tech Nottingham for that. They sponsor our Zoom license, so that's good. As I mentioned before, JetBrains, they're sponsoring us a license to one of their products. So if you tweet on the hashtag NotsIoT, at some point in the next few days, I'll draw out a random person called Alan Buxley to win one of those JetBrains licenses. And they're really good though. So thanks to them for that. So tonight we've got Dr. Mike Pound from Nottingham University and computer file fame talking about cracking the Enigma machine. But coming up next month, this is, they've not responded back to me about this, but they did say they were going to do it. But Jorge Ramirez from Wilderness Labs is hopefully coming along to talk about what they do with their IoT tech, which is quite cool. So they've got full .NET on a Arduino scale device, which is pretty cool. So it'll either be the 8th of July or later on in August. It just depends on what actually happens with that. On the 28th of June, we've got a .NET Foundation takeover with Beth Massey and Bill Wagner coming along to talk about what the .NET Foundation are doing. So that's going to be a really cool meetup. I'm really looking forward to that. So in fact, what's that, a week on Monday? So not long for that one. If you like IoT, then check out the IoT Live channel on Twitch. We're part of the Azure-ish Live channel on there, and it's mostly 9 p.m. BST on Tuesday nights, and then for a sort of a hands-on lab type environment on Thursday afternoons. We're taking a break from that at the minute. Likewise, Louise Gulliver, Jonathan Rolfe, Misha Bell, Liam Gulliver, and myself are all part of Louise Palin. Did I say Louise Gulliver there? That's pairing you off there.
You did. I'm not sure his fiancée would be best pleased about that.
No, probably not. No, but now everybody knows. So, but we run an agile and DevOpsy type podcast that's pretty good, even if I do say so myself. So go and check that out. And also, I've created, along with a bunch of other authors, some Pluralsight courses on the Microsoft IoT Developer AZ220 exam. And in fact, I think either tonight or tomorrow, my latest course will be released in that series of courses. So go and check that out too. And that's that Agile Engineering podcast just there. So go and check that out. And with that, I will pass across to Mike to talk about the Enigma machine and how to crack it.
All right. Well, thanks so much. Yeah, so I did a video on Enigma, and that's when Pete contacted me. So if you've watched the video, then obviously you've seen me attempt to break Enigma. Now I've sort of done some slides and tweaked the code a bit. I've been improving some things, so we'll take a look. I didn't crack Enigma specifically to do a YouTube video on it. That was a side effect. I just quite enjoy doing things like this in my spare time. I don't get to code as much because I've sort of moved, dare I say, into a slightly more managerial teaching role, less of a sort of low-level developer role. So it's fun to mess about with code. Right now, I'm going to share my screen. I'm going to share the whole screen because otherwise I'm going to be constantly trying to move between windows. So, if things are too small or I accidentally minimize everything like I just did, then, let me know. There we are. So I've got a few slides, but they're mostly just pictures, so I can talk about kind of my thought processes when I was trying to break this. I'm coming at this from a kind of modern standpoint, in the sense that I'm not super expert in the way that I know how they broke Enigma originally and things like this, but I'm not a mathematician. I'm not as smart as Alan Turing by quite a way, so I haven't worried too much about that. I've just done my own thing. I've got a laptop that's much more powerful than his computer, so I'm at an advantage. What I was hoping to do was, and please do ask questions or just tell me to talk about something else, is a little bit of a look at how an Enigma machine works and how that helps us break it. And I'm going to reference a little bit of cryptography theory, but only very, very little bit, just because I think it's interesting and kind of relevant. So most of you will know what an Enigma machine is. There are lots of pictures online, so I found one. And you've got the plug board down here. I don't know, Pete, if you can see my mouse. Hopefully you can, so I can point around. But if not, then I will.
We can. It's small.
It's small, yeah. Sorry, I've got a 4K monitor from work, and it doesn't help. So you've got the plug board down the bottom. We'll talk about that later. It's a pain in the rear end for trying to get things to break Enigma. You've got the keys, the lamps, and then you've got the rotors. And essentially what happens is it's a purely mechanical device. It's not a computer. You press a key, the rotor rotates, and then a lamp lights up. Right? And it does this because there's a circuit between that key through the plug board, the rotors, and back to the lamp. Right? That's essentially how it works. And it's not very easy to break this device, right? The encryption is done with this device because it has quite a large key space. That's essentially the problem with it. And most of it comes down to these rotors, right? So this is an exploded diagram. This is two rotors, actually. There's a rotor on the left and there's this exploded rotor on the right. I think, most people are familiar with what it is, but essentially you've got 26 pins in and 26 pins out. The rotors connect together and then they can rotate, connecting different pins to different pins and things like this. And you've got this wiring inside, which allows you to go from A to F or, Z to Q or, whichever, depending on what the rotor is. Now, I'm going to talk a little bit later about some of the other intricacies of its rotor. But this is essentially a substitution cipher, right? A bit like a Caesar cipher, except that the translation between each letter is arbitrary rather than all shifted by a certain amount. And that on its own is not a very good cipher, right? Because essentially the same weaknesses apply to that kind of cipher as apply to things like the Caesar cipher, which is essentially that you can do frequency analysis. You can say, well, this letter is the most common. That was probably the E. And then the next most common was probably the T, and so on. And so it doesn't hold up at all. What makes the Enigma machine complicated is the fact that these rotors can rotate. And that means that the mapping from input to output changes every character, which means that you don't have sufficient time in one character to build up an idea of what letters are the most common and this kind of stuff. That's essentially what makes it difficult. But yes, the key space is quite large, mostly because of the plug board. But as we'll see, and what I was working on when I was trying to break this is that actually you can kind of ignore the plug board to begin with, and that makes breaking it much, much easier. All right, so each character, when you press a button on an Enigma machine, what you're actually doing is essentially a monoalphabetic substitution. Right? That's a technical term. So you've got, this is rotor 1. It goes from A to Z, and that maps to these particular characters here. Now, this is actually the rotor 1 wiring. So you didn't make this up. You could use your own rotors in Enigma, but the Germans obviously didn't, because if you use different rotors to everyone else, you're not going to be able to read their messages, and that was kind of the whole point. So in this case, for example, H goes to Q, E goes to L, and so on. So you get this Q, L, T, T, Y that comes out when you use just rotor 1. Right? Now, there's nothing complicated about this substitution. It's non-linear to an extent, but basically from a sort of cryptography point of view, it's very, very predictable, right? Very, very easy. But when that rotor rotates, what essentially happens is all the letters on the lowest row move one to the left or to the right, and then they wrap round. And that means for every character, you get a slightly different mapping. And because you're not just shifting everything by the same amount, it's slightly unpredictable. And that makes it a little bit more difficult to work out what's going on. So you can chain multiple rotors together. And this is exactly what an Enigma machine does with either 3 or 4 rotors. I've only implemented the 3 rotor one, mostly because I was lazy and couldn't be bothered. Not because it wouldn't take any much longer, really. So H goes to Q. This connects directly to the input of the next rotor, which in this case is rotor 3, and that maps Q to I. And so you get a different mapping from hello to this IVAAQ. Right? But the thing to realize, I suppose, about this is that when you just put multiple rotors together, they just become another bigger rotor, right? It's linear functions added together. It's just a different linear function. That's what's happening here. So you could replace these 2 rotors with a new rotor that had a different set of mappings that represented the same as both of them, right? So just having rotors one after another doesn't make it more secure. Right? It's just what makes it more secure is because they're all moving in at different rates. So, from a programming point of view, this isn't too complicated to implement, right? So what I've done is, if I can find the place where I put it, this is my code. I started actually not trying to break Enigma, right? Because the resources on breaking Enigma online are not very good. There's not very many of them for 2 reasons. One is that most of the resources about breaking Enigma refer to what they did in the war, sort of historical stuff, and that's absolutely fine. And then also, most cryptographers are not breaking Enigma. They're trying to break modern ciphers, right? Because they're the ones that are actually being used. But I'm more interested in this just from a sort of curiosity point of view. So I began by just implementing it. And I was implementing a number of algorithms, modern and historic algorithms, just to sort of get to grips with them. I'm going to be teaching cryptography next year. So knowing how all of these things work, even if I don't end up covering them, for things like Enigma, is good for me. So this isn't too difficult to implement. The problem you have is that you very quickly run into array indexing problems, right? So I'm going to, hopefully you won't mind if I show you a bit of code to walk you through what I did. But essentially I used, Java object orientation to try and do this to make my life a bit easier. If I just make this a bit bigger, hopefully you can see it. So these are the definitions of rotors that they used during the war, because there's little point in implementing my own Enigma machine if I can't read and write messages from other Enigma implementations. Right? Plus, I was using other Enigma implementations as a test bed. Right? So I wrote a bunch of tests based on output of other Enigma implementations with a view to trying to make mine correct. And I did not get it right the first time, I should add, because there's a lot of weird stuff going on sometimes with some of the rotor positions. So this is fairly straightforward, right? When you create a rotor, you give it an encoding as characters. Now I didn't have to do that, but it was just easier to look at, right? And then down here, I actually decode the wiring into an array. So each rotor is just an array of 26 values. And so A is 0, I use 0 indexing, Z is 25, and then you just look up whichever character you are, you look it up, and that's the one you're going to connect to the next rotor. And then you can just chain these rotors together by just doing repeated array indexing operations. So it doesn't take, it's nice and quick. A lot of the Enigma implementations online implement this all using strings, and they actually physically rotate the strings every time that you get a turnover and things like this, and it's unbelievably slow. It's nice from a sort of actually implementing an Enigma machine in code, but I wanted to try and, after I started implementing this for a little while, I thought, okay, I might try and break this later. I want it to be quite fast. So I wanted to try and do the absolute minimum of moving things around. So you basically, things are a string on the way in, and then they're no longer a string, right, after that. They are just numbers. So I'll talk a little bit about enciphering in a little while, because it gets a bit more complicated with the ring positions and the ring settings and the rotor position. But essentially, it is just array indexing with a lot of modulo to make sure you don't accidentally go off the bounds of an array. How does an Enigma machine work? Well, if you don't know, it works a little bit like this extremely complicated diagram off Wikipedia, which I've simplified somewhat by removing a bunch of stuff. It's actually a very good diagram. It's just, when you first look at it, you think, crikey. It's a purely mechanical device, as I say. So you press the A key, and that switch comes down, and you get a flow of current from the A into the rightmost rotor. So on the right here, you've got the entry board. So this one on the right. These are the 3 rotors in the middle, and then you've got the reflector on the left-hand side, and it's just an electrical circuit. So each rotor maps a character to some other character, and it's rotating, so you don't know, obviously, what that mapping will be. So this one maps from the bottom to the top, then from down here, and then we follow it along, and it goes all the way around, and then that lights up the lamp at D. Now, there's a few interesting properties of this that we'll perhaps go into a bit more when we talk about breaking it. But essentially, A goes in at this position of the rotors, A goes to D, and if you lifted up A and press D, then D will go to A, right? We're just ignoring the fact that rotors rotate. So there's a sort of reciprocal encryption here, which has an advantage from the way that Enigma works, because you can just type in the ciphertext and you'll get the plain text back out, right? Which is, from a usability point of view, very, very convenient. From a security point of view, it's not so convenient, right? Because you have these issues of A can never encrypt to A, which is a problem. We'll talk a bit about that. Actually, the attack that I use doesn't rely on this at all, right? But it was very, very important during the war when they were breaking it based on cribs. I've completely deleted the plug board from this diagram because it overcomplicates things. But I have got one in there, and it's here. Okay. Same diagram. Now there's a plug board. All the plug board does is exchange certain characters. So essentially, it removes certain bits of circuit and plugs in different bits of circuit. So now the A goes through the A, which is not plugged, up through the rotors, and then when it returns, it goes into the S, I think, according to this diagram. Yeah. And that goes to D, which lights up. Right. So the plug board is another monoalphabetic substitution, which is applied before you go into the rotors, and again when you come out of the rotors. And what makes the plug board, because I mean the monoalphabetic substitution is not interesting in and of itself, but what makes it, what makes Enigma much stronger is the fact that you don't know what that substitution is going to be, and there's many different possibilities. In fact, there aren't that many combinations of rotors and positions, but there are a lot of combinations of plugs, some 150 trillion for 10 plugs, for example, and it makes life a lot more difficult. Now it's an oversimplification to an extent, because if you get 9 out of 10 plugs, your ciphertext decryption is going to look pretty good, right? Because most of your characters are going to be correct, so that's worth bearing in mind. But when you hold on a minute, Hello. All right. I'm just doing a talk in here, but they'll come and answer the door for you. Got the door going. Problem with working from home is that, you get postmen and you get people coming, delivering one of my kids back from a play date and so on and so forth. All right. So, so getting some of the plugs right will help. But when you're trying to get the rotors right with 10 unknown plugs, this becomes a real problem, right? And a real challenge. Okay, let's talk a little bit about turnover then, right? Which is the thing that makes Enigma really strong. When you press the key on an Enigma machine, some pawls at the back, which are essentially three little pokers, rotate at least one of the rotors around, right? Based on this ratchet on the left. So these are two sides of the same rotor. And on the left, you can see the ratchet mechanism. So essentially a pawl pushes at the ratchet and just rotates it one step. The outer ring is just used to keep it aligned, right? There's this little groove that things sit in. So when you press the, and so from an implementation point of view, when you press this, it rotates and then you send it through the arrays and you perform the encryption, right? You don't encrypt first and then rotate, which is an easy implementation mistake to make, which I made myself. So in the code, for example, you would see that I've got a code. So I know where so when we turn over, we just move the rotor position, we increment the rotor position 1. That's so far so good. And then when we go forward, what we have to do is we have to calculate a shift into and out of this array. So if you think about, if I go back to my diagram, if you think about this rotor with its 26 positions, that's the array fixed. We're actually rotating the rotor around. From a programming point of view, what we're actually doing is just shifting our index in and out. So we have our 26 long array. We're going in here. So instead we go in and shift over here. We go through the array and then we shift back again on the way out. So it's just like shifting the whole array or rotating the whole array. But by doing it through just array indexing, I was avoiding actually physically rotating the array every time I turned over, which would have been really, really slow. And as we'll see later, speed is of the essence when you're trying to brute force this. All right. So the right-hand rotor rotates all the time. Right, so far so good. I did an amazing, or I think is an amazing PowerPoint diagram of this in a moment. PowerPoint was not meant for these kind of diagrams, but I was pleased with myself. In fact, let's skip. Yeah, there it is. Right, that's the absolute best I can do in PowerPoint. I should have used Inkscape or something else. This is the back of an Enigma machine. So you've got the right-hand rotor is the one on the left because the keyboard's the other side. So these pawls go up like this every time you press a key, and the one on the left is engaged, but the red is the ratchet. So I didn't get as far as drawing in all the little cogs. So sorry about that. So whenever that pawl pushes up, it rotates that rotor forwards 1. Right, so far so good. So every time you press a key, it rotates the left-hand rotor. Now, if you look at the rotor on the very right-hand side, that pawl is not engaging with the red ratchet because the blue outer bit of I can't forget what it's called, of the middle rotor is holding the pawl back. So essentially the pawl is resting against both the middle rotor and the right-hand rotor. It can't engage with the ratchet because it's stuck on the middle rotor, right? Whereas it on the left rotor, you can see there's a notch. That notch, the pawl has fallen into the notch, and that means that when that pawl moves up, it's going to rotate the middle rotor. And that's called a turnover. So the rotor that's physically on our left, which is the fast rotor, is rotating every single press because there's nothing to stop that pawl from engaging with the ratchet and rotating the rotor. The middle one is going to rotate this time, and then the left rotor will move out of the way. There'll be no more notch there, and it won't rotate for another 26. Right? That's how the rotation mechanism works. And then the right-hand one, you can see a notch on the right, has no effect because there isn't a fourth rotor. Now, the real pain with implementing this, apart from knowing whether a notch is at 16 or 17 in your index, but that you can just kind of learn by doing and just program it in. And if your encryption's off, you know that you've done it wrong. The issue is something called double stepping, right, which is very difficult to find good resources on. So what's confusing is if you look at this situation here, right, which I have, so this is a new diagram. We've now got the middle rotor notch engaged with the pawl. So what's going to happen is this is going to turn over the right hand, a slow rotor. Now, it's also the pawl going to push against the notch and turn over the middle rotor. So when the middle rotor turns and engages the notch, it's going to turn again the next press. So you get a double step of that middle rotor, right? It's very easy to miss that when you're implementing it. And indeed, hardly anyone talks about it because it's just sort of this sort of minutiae detail of Enigma that unless you were coding the thing up, you wouldn't need to worry about, right? I'm afraid I haven't animated this because look at the state of it. So essentially, the right-hand rotor, I mean, it's right. I shouldn't have done my diagram backwards. The fast rotor, which is the one on the left of your image, is rotating every click. The middle rotor is rotating one every 26 when the notch on the fast rotor is engaged. And it also, and there's now an alarm on my phone going off. Why is it? It's just to tell me it's 7:15. That's very helpful. Thanks. And so the middle rotor actually rotates twice in quick succession, right? The right-hand rotor rotates one every 26 times 26, and it never rotates anything because there's nothing behind it, right? So how did I implement this? Well, it was a pain, I'll be honest with you. But mostly it's just about remembering when your notch is. So all of the German Enigma rotors have their notch defined in, should we say, in the spec. Where is it? So this is my rotor code. And you can see if I scroll up, I've defined where all the notches are for each individual rotor. This is 0 indexed. And the notch, remember that when the pawl engages with the notch, it turns over on the next press. So you don't write an if statement that says if you're at the notch, turn over. You say if you're at the notch and it's been pressed, you turn over, right? So it's just about making your if statements in the right order, not messing it up. Again, these are the kind of things that are going to throw you if you're implementing this. But you just practice until it works. Right? The rotors 6 through 8 have 2 notches, which actually is a little bit weaker cryptographically, but not for really what I'm doing. So that's all there is to it. I mean, you have an if it's notch, which is if your position is the notch position, then you're in your notch. And then if you go into the Enigma machine that I've implemented, if I make this nice and big, you can see that my implementation is pretty straightforward, right? I'm encrypting some character, which I've now moved from 65 to whatever, which is, the actual character encoding to 0 to 25, through the plug board, forward through the plug board, forward through all the rotors, forward through the reflector, backwards through the rotors, backwards through the plug board. That's it, right? And then each of these forwards is just performing, where is it? There we go. Is just performing this shift and array index. That's all it's doing. I will mention the ring setting in a moment. I'm trying to introduce things as we go rather than all at once. I'll tell you what, it took me a good couple of hours to get that ring setting maths correct, because even though it's incredibly simple here, it just trying to visualize in your head that the rotor's turning and the internal thing can shift because of the ring setting. I did not enjoy that. Right, this is the Enigma machine. So when we rotate, if the middle rotor is at the notch, then we would turn over the middle and the left. The left is the slow rotor because of a double stepping. If it's just the right rotor at the notch, we just turn over the middle rotor, right? And the right rotor always turns over, and that's it. If you wanted to do this for a 4 rotor Enigma, you just have to add an additional if statement. So fairly straightforward. I pretty much always use reflector B. There's 2 that the Germans used. Okay, let's see what my next slide is, because I don't remember. Oh, yes. So what's the difference then? Now that we've got stepping and turnover and all this kind of business, cryptographically, what's the difference? Well, this is now a polyalphabetic substitution. This is what an Enigma machine does. It's essentially a monoalphabetic substitution per character, right? So think of a Caesar cipher, except that every character you do a different amount of shifting, right? And obviously the shifting is more complicated on an Enigma. So H might go to Q, but if you put in H again, your alphabet's going to have changed and you're going to go to a different letter. And this completely basically defeats frequency analysis of a ciphertext, right? On a Caesar cipher or a monoalphabetic substitution, you would just look at how many different characters you had and work out what the E was and what the T was and what the A was and go from there. You can't do that on this because you have literally one example of each, which is, you know, that character. And the cycle of this is roughly 26 cubed. Because of a double step, it's actually 26 times 26 times 25, but it's big. And so the cycle is very, 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 very long. There's no messages of that length. So you're never, ever going to be able to do frequency analysis. There were historic ciphers like the Visionaire cipher, which have a running key, and you can do frequency analysis on, let's say, every 7th character or something like that, and start to break them. You can't do that on Enigma. And that's what makes it strong. Its weakness from a modern point of view is still the fact that it's one-to-one. H goes to Q, E goes to X, but there's no movement between characters like there is in a modern block cipher or anything like that. In a modern block cipher, if you change that H, all of the outputs will change, which makes determining exactly what just happened here really, really difficult. Okay, I have a picture of a Turing bomb, which we spoke about earlier. There's going to be people in the audience who know much more about Turing bombs than me. But this is an entirely different way of attacking Enigma, much more clever, I should say. But during the war, they didn't have laptops that could brute force through keys. So what they did was they tried to find all the possible rotor positions where, technically speaking, some plain text could have worked, is essentially what they did. So it was a known, what we would call a known plain text attack. So maybe they have the word weather report. They use the fact that you don't know where, they use the fact that they know a character can't encipher itself to work out where the word weather report could be. And then they come up with something called a menu with the plugs at the back of this. And each of these columns of 3 is an Enigma machine with the fast rotor, the middle rotor, and the slow rotor. And the different colored rotors are a different, like 1, 2, 3, 4, 5. And essentially, it just spins them really, really quickly and goes through all the different possible positions, a bit like what my code will do. But it's not looking for a proper decryption. It's not examining all the ciphertext or anything, or the plain text or anything like this. What it's doing is it's seeing whether, technically speaking, that could have worked, right? Whether the plain text, whether the ciphertext is coming out, whether there's any logical inconsistencies with what's been enciphered into what. And then if it stops, it's because one of these, should we say, consistencies has been found. And then the gold rotors on the right-hand side, they tell you what the current setting is. And then that doesn't break it. What you do is you take that possible starting position and you give it back to someone in a hut who painstakingly actually works out which of the stopping positions was the correct one, where the ring settings were, and things like this. So this was a very, very clever brute force of some part of the key, right? Because the key space is so large. So it had the advantage that it could do this without knowing what the plug board settings were. Which is kind of what mine does, sort of, apart from the plug board still makes things really, really difficult. All right, so how do we actually break Enigma in 2021 with my laptop, right? Or as we shall see, with my large high-performance cluster. These are the 3 rotors. Now, these have been swapped around from my diagram because I've decided to just pick a load of images that are confusing for everyone. So this is now the front of the machine where we're sitting. And you can see the notches at the back. The pulls are coming at the back. So the fast rotor is on the left. No, it's not. Hang on. No, the fast rotor is on the right now. There we go. I got it. Fast rotor is on the right. Slow rotor is on the left. We have, let's say, 5 or 8 different possible rotors, which are sort of hard-coded and hardwired up. They can take any position from left, middle, or right. So you might have 1, 2, 3. You might have 3, 2, 1, 1, 2, 5, right? So there are 60 possible combinations of 3 rotors out of a possible maximum 5. Right? So that's the first part of the key space, 60 possible rotor positions, configurations. You then have the rotor starting position. So the rotor can rotate. It rotates every time you press a button, but also you can rotate it at the beginning as well. And finally, you have the ring setting, which is where you actually take off those numbers and slide them around. And what that does is essentially rotate the internal wiring symbolically. And it to an extent cancels out the initial position, right? If you move the ring setting 1 and then you rotate the whole rotor 1 back, it's going to be the same. But what it does do is it moves the notch. That's the thing it does. So it changes when that the fast rotor turns over the middle rotor, which completely changes your encryption, right? But not entirely, because you might luck out and maybe for 5 or 6 characters, the middle rotor is in the right position before it incorrectly rotates or doesn't rotate quickly enough. So a little bit of plain text might bleed out if you get the ring settings a bit wrong, but the rotors are correct, right? And that's what we're going to exploit. Then you have this problematic plug board that just switches characters at random, both on the way in and out. What a nightmare. 150 trillion different combinations. So your total search space is 10 to the 23, which I think it's a sextillion. There are two, I didn't mention, there are 2 possible ring settings. So there are 2 ring settings, each of which can be 26 values. The ring setting of the slow rotor makes no difference because it affects where the notch is and it doesn't turn anything over. So we don't need to worry about that. So we've got 60 rotor positions, different rotors, 17,500 possible rotor starting positions, 676 different rings, 150 trillion different plugs. That's quite a big search space, even for a modern laptop, right? Or indeed, even for a modern world's fastest supercomputer. So we don't tend to attack this search space directly because that would be ludicrous. Right, let me just go back to my code briefly. Do drop questions in, by the way, because I can't see the chat, so that's no problem. So the only thing I would show you again is I've got this shift here with the position minus the ring. So essentially the ring works to counteract the position to an extent, but it also affects where the notch is. Right. And when we go in, this mapping is our lookup matrix of our wiring. We go in at a position K, we shift along the rotor, which is essentially symbolically rotating the internal wiring in the rotor. We look it up in the index to find out where we're coming out, and then we shift it back again, right, to make it align with the previous rotor. This for 1 or 2 lines of code took me quite a while, because if you get that as a plus or a minus in the wrong place, it just gives you complete nonsense out, and it's very difficult to debug. But we got there in the end. All right. So encrypting, like I say, is pretty straightforward, right? I haven't talked about the plug board, and I will in a moment, but basically it's just forward through them all, through the reflector, and then backwards. Right? The forward and backwards terminology I like because it comes from machine learning. So it looks a bit like a neural network to me. All right, the plug board is very straightforward. It's just another monoalphabetic substitution. So all I do is I take characters like this. So it's something like, A, Z, T, B, F, E, and I just take pairs of characters and I turn that into a 26-digit lookup table, and the reverse of which, so I can go backwards through it as well. Although actually you don't need to do that in a plug board, of course, because it's reciprocal. So you just have to have the one forward. In fact, did I implement that? I must have done. Forward, yeah, just return wiring. Oh, it doesn't have a backwards, that's why. All right, yeah. See, I've confused myself with my own code. Okay, so how do we break this? Well, the nice thing about these are the weaknesses that I think are relevant, right? So there's one that everyone talks about, which is letters don't encrypt in themselves, and that is a weakness, but it's not a weakness for a brute force key search, because I don't know what the plain text is. Right? If I knew what the plain text was, I could say, well, okay, so this letter's encrypted to something I was expecting. That can't be right. But that hasn't happened because I don't have the plain text. So in the war, they relied at Bletchley on having some plain text guesses in order to break it. They couldn't have broken it without that. Now we don't need plain text guesses. All we need is some way of saying, okay, this is a better decryption than we had a minute ago. We're moving in the right direction, and I'll talk a bit about that. But there's a few weaknesses. The plug board sometimes doesn't do anything. That's the biggest weakness. So if you've got 10 out of 13 plugs, right, then that means that 3 letters just encrypted themselves or decrypted themselves, and they're called unsteckered. So that means that some small percentage of the time, if you got your rotors exactly right with the exact right ring settings and the exact right position, that plug board, for those for those few characters, it's just going to not do anything, right? And that's useful. The other thing that might happen is your plug board, about 4% of the time, will cancel itself out. So it will change a character in such a way that it comes back out exactly what it was meant to, right? Because if you think, so S goes to D here, well, if the if it comes back out as D and goes back to S, it's kind of undone itself, right? That's kind of the idea. 1 in 26 chance of that happening, basically. So 1 in 20, so about 4% of the letters will come out as they were intended as plain text, and the ones that are unsteckered. So if you have a 600 character encryption and you decrypt it with the correct rotors, even with a plug board, you'll see a little bit of text that comes out. Not a lot, and probably not enough to read it, but a little bit of text. And that's all you need on a laptop, right? To start getting, I say it's all you need. I mean, it doesn't work half the time, but it works some of the time. And if you've got longer text, it will work much more of the time. And the other thing is about this ring settings, right? So if you get your ring setting wrong, then what happens is essentially your notch is in the wrong position. So the middle rotor is going to turn over too soon or too late, right? And the right-hand rotor, the slow rotor, is going to turn over slightly too soon or slightly too late. But it's not always going to do that. And sometimes for some amount of characters, it's going to be correct. So what you'll see is windows of correct plain text, and then windows of gibberish, and then window of just like a couple of words or half a word or something like that popping out, where just for a bit they were in the right position, and then they go back to being in the wrong position because of the turnover. So those are some pretty big weaknesses. They are not weaknesses shared with modern encryption, right? But this is much more interesting. Yeah, so that's good. So the key question to begin with is, can we determine, given these weaknesses, the correct rotors? If we can just get the rotors in the right order, maybe we can get some plain text out. That's our idea. So what we do is we split our key space into 2 or 3 to make it much, much smaller. We essentially completely ignore the plug board for now. It's much too big. Let's not dwell on that. What we do is we take the ring, we take the 3 or 5 rotors, we can brute force through that. That's 60 possible positions, 17,500 starting positions. That's the rotation of the rotors, is about 1 million different positions. So we have 1 million positions to analyze in some way. And then once we've got the best of those, we can look at the 676 ring settings and find the best of those. And then we can start looking at the best plugs, and we can work our way down through this list. So that's the real problem with Enigma in 2021, is that you can split the key space in 2 or in 3. You can't do that with an AES key. You can't do that with a char key or any modern cipher, because if you've got 256-bit key and you try and brute force the first half, it won't work because you don't know what the second half is. Whereas in this, it kind of does work, and that's the problem. If it didn't, we'd be in real trouble. So how do we brute force the first half, right? Because we still haven't solved it. What we need to be able to do is, for a rotor position, we need to put it through the Enigma machine and see if what comes out looks any more plausible than when it went in. Right? We know the ciphertext is wrong. So is it a little bit more like possible plain text? And this is under the assumption that we don't know any actual words in the plain text, right? It's not known plain text. It's called a known ciphertext attack, which is the weakest attack cryptographically. So here's 2 examples, right? Now, let me know if you need me to make this bigger. You don't need to read this. It's gibberish, right? But what we've got here is some fitness functions. Now, a fitness function is a function that measures, in essence, the Englishness of this text. Right? It's Englishness because I've run it on English statistics. You could do this for any language. So the top is some ciphertext, and the bottom one is some ciphertext which has had the rotors in the right position. I don't know, and maybe the rings are even in the right position. I can't really remember. And I've used a few different measures of fitness. Right, so the one on the left is called index of coincidence. I put my slides in the wrong order, by the way, because I'll tell you what an index of coincidence is in a minute. We've got index of coincidence on the left, and we've got a slightly higher index of coincidence for the slightly better text. Now, to me, that I can't see any words in that text at all. Right, that's kind of the whole point. But it's just a little bit more like plausible English text. I mean, in a way, it's equivalent to frequency analysis, right? You're looking for more E's, you're looking for more T's, Maybe it's got slightly more E's and T's than the other one. Bigram scores are the probability of different pairs of characters. So for example, the character pair TH, as in the, much more common in the English language than the character QZ, which hardly ever comes up, right? And so all you do is you go through your text and you look for all the different pairs, and you multiply the log likelihoods together, and you get a probability of that whole sentence. And the probability, negative log, of the top one is minus 2,500. The one below is slightly better. It's minus 2,200. And you're never going to get zero. It get the higher the better. And the same for quadram scores, which are quadruple characters at once. So I got a bit carried away when I was implementing this. So if I go into my code, what I did was I implemented a fitness function, which is just a, hang on, make it bigger. Right, this is just an abstract class which allows you to score some text. And then I implemented a bunch of different fitness functions. So for example, the known plain text fitness function is where you type in some actual words and it tells you, essentially it gives you a better score if the words are in the correct place, right? So if you've got characters that match where you think the plain text is, you get more points. I think it's literally +1. Yeah, there we go. Look, if your plain text is in the right place, you get 1 point. Otherwise, you get no points. And so the more characters you have correct, the higher the score will be, the higher the fitness will be, right? We're not using plain text fitness because we don't know what the plain text will be, but you could. All right, so what's another one? Well, let's look at the index of coincidence. So the index of coincidence is where you, hang on, I've actually got a slide on it. There we go. The index of coincidence, which was actually, it already existed actually previously to the war, and it was the reason that the Germans had quite a clever keying mechanism for their messages, was because they already knew about the index of coincidence and they knew it could weaken their messages. Essentially, what is the probability, if you've got a random string, what is the probability of drawing 2 characters at random from that string and then being the same? So you pick a character at random from your string and it's Z. What's the chance of it being another Z? Well, for a random string, it's about 1/26, because the chances of it being the same are exactly how many characters there are. But for English text, that isn't the case. There's lots more E's, for example. So if you draw an E, the chances of you drawing another E is not 1 in 26. It's slightly better than that, right? And the average for English text is about 0.067, right, or about 6% rather than about 3%. Now, that is a very, very subtle difference, but it's actually quite telling. So what you do is you calculate the frequencies of all the different characters in your hypothetical decryption, and then you calculate this index of coincidence, which is very, very trivial. And you say, okay, well, it's a little bit better than 0.038. So it's not quite as random as it used to be. Or maybe it's getting close to 0.067, and so it's looking a bit more like English text. Actually, German text is 0.072, so it's even more predictable. If you're looking for an intuitive idea of what index of coincidence measures, I heard it described as the spikiness of a distribution. It gives you benefits for having some characters appear more regularly than others. The more uniform your distribution is, the less interesting the index of coincidence is. These are some example n-grams. I already explained these. So these are the top, I think, 10 or so n-grams for 2, 3, and 4 characters. And so TH, unsurprisingly, and THE are the most common 2 and 3 characters. Shun, apparently, is the most common 4. These were actually calculated over Google's entire book repository. I didn't do it myself. Someone from Google did it. I can't remember off the top of my head whether it was to break Enigma or not, but anyway, I found them on the internet and I downloaded them. These are represented as log base 10 because then you can sum them up. You don't have to do multiplications. It's marginally faster, but essentially think of these as the higher the number, the more likely it is. By the time you get down to the least common letter pairings, we're talking about something like -9 or something like that, and you're multiplying all these together. Adding all these together, to be clear. So this is why you get scores of in the -2000s for a sentence, because the longer your sentence is, the less plausible it is as a sentence, because there's lots of other possible sentences. So it's literally based on the frequency of all text that Google's ever seen. It's the probability of that sentence existing, which I think is quite cool. only for English because it was done on English text. So I implemented these, not too complicated because I pre-computed all the likelihoods and just stored them in a text file. And where are they? Somewhere in my resources, which is, here it is. There you go. And it's quite long. I shan't show you it all. So all I do is I go through each pair of characters. I read out of my array and I add them all together, and that's my by diagram score. So each of these fitness scores works exactly. This is my quadram one. Works exactly the same way. I've just done a little bit of array indexing to try and make it a bit faster, but so I don't have to repeatedly read characters from the same place in memory. And all I'm doing is going through groups of 4 characters, reading it out of the index, and then finding out what the likelihood is and adding them all together. And that's the fitness function. Okay. So how do we actually break it? Well, it's fairly straightforward then. What we do is we go into main. Hang on, let me clear some stuff. There we are. So this is my ciphertext, which I generated just for today. So it's not the same one in my video. It's all very exciting. It's not that exciting. So what I'm going to do, we write a loop that goes through all the different rotor configurations. We pick the best rotor configuration and we optimize its ring positions. And then we take those and we optimize the plug board. And I'll talk about that last. So I wrote some classes to do this. So I've got this function that calls find rotor configuration. It takes a ciphertext, the maximum number of rotors I'm going to allow. I could do it out of 8 rotors if I wanted, but it will just make this slower. So I can't. It won't really. It doesn't actually hinder the break particularly, especially if you've got a long ciphertext. No plug board. Get the best keys. Get the best 10 keys. And we're using the index of coincidence for this. As a side note, I found that index of coincidence works much better for this initial bit than any of you'd assume that quadram scores are really powerful and they're much more interesting. They don't work for very plugged, very badly configured rotors, because even if you get one character right, those 3 characters next to it are not going to be right, and so your quadrams are all over the place. Index of coincidence just measures whether it looks a bit less random. That's useful. So what I actually do is I use index of coincidence first, then I use bigrams, then I use quadrams, and I work my way through, becoming slightly better as we improve the break. So if I go into my Enigma analysis, I don't know why the default font size is so small. I mean, this is not rocket science code, right? But some loops for different rotors. I create a new Enigma machine and I measure its fitness. And if it's better than the previous fitness, we're on to a winner. Right? Now, because I'm going to optimize the ring settings later, what I actually do is I set all the rings to 0. So I put all the rings at their default positions and I just rotate the rotors. This means that the notch is almost certainly going to be in the wrong position. But as I say, bits of text will bleed out and it will look okay. When we get to the end, all I do is I have an Enigma key, which is a class that holds the rotor positions, the ring configurations and things like this. And then I have a scored Enigma key, which is a subclass that just adds the score. And I have a huge list of these. There are not that many. There are only 60 different possible rotor orderings. So all I do is I have a list of 60. And for each of those, I keep only the very best starting position. So let's try it out. We're going to main and I'll put a breakpoint in, otherwise we'll get ahead of ourselves, and pause it about there and off we go. Now, this will take a small moment where I'll just vamp to ask a question. So you can see in the bottom left, it's very small. I don't know if I can zoom in on this. I can, yeah, actually. It's going through the different rotor positions. And for each of these, it's doing all 26 cubed starting positions. For each of those, it's decrypting the entire plain text and calculating an index of coincidence. So there's quite a lot of work this computer's doing. It's just that modern computers are really quick. So it doesn't, I thought it would be slower than this, but I'm always astounded by modern computers. Also, I haven't made any effort here in terms of threading, right? This is a single thread just working away. This takes a little bit less time because we're only doing 60 configurations of rotor, not the full 300, which is the 8 rotors. So on rotor 4 on the left, so they represent left to middle to right. And it won't take long because we're on rotor 5 already. And then it will spit out the best 10 rotors. I've already forgotten what I noted what my rotors were here just in case I forgot. So I think it's 253. Where's my console gone? I still don't really know how to use IntelliJ. There we are. These are the top 10 rotor configurations. Oh, it's 315 apparently. 314. Oh yeah, it's because that's completely a different plain text from earlier. Sorry. So I think it's 314. At least I hope it is, because otherwise this is totally failed and you should pull the YouTube stream and we'll just pretend it didn't happen. Now, in practice, what I'm actually going to do here is continue from you assuming these are correct. What you would actually do if you had a very difficult message to break is you would look at the top few, perform different analysis on each, and try and work out the best solution. I've automated this. You don't have to automate it all. All right. So what am I going to do next? Well, I'm here, and I've now got the best possible rotor configuration. So we know, or we think we know, that the rotors in use were 3, 1, 5, 4 in that order, and their starting positions, or the best performing starting positions, were 3, 17, 9. So now we're going to stop those default ring settings and we're going to move them around, and that's going to change the turnover. So if we go to our Enigma analysis, this is much quicker now, because all we do for the ring settings is we optimize the right hand ring setting and then we optimize the middle ring setting. So it's literally a loop of 26 followed by another loop of 26. That does not take very long because you can optimize both of them separately. Again, we don't try and optimize the slow rotor because it doesn't turn anything over. So its ring setting is entirely unrelated to anything. So let's see if that works. Where's my code gone? There we go. So I'm going to break in here and I'm going to, oh, incidentally, this is our current decryption using this rotor. In fact, actually, I've got something I can show you. So no, not that. I've got too many command prompts. Apologies. There we go. Right. What I did just for today, I wrote a very, very simple Python script that will just look at 2 strings and tell you how many characters are the same, right? And show you the string, like a diff, right? Because I couldn't find any diff tools that did character-wise comparisons. I mean, I'm sure there are some, but I didn't want to pay anyone any money for it. So if I do a diff of the plain text and the ciphertext, you might be able to guess how many of those characters are going to share. Precisely 0. Because by definition, Enigma never encrypts to itself. So the entire string is blank and no character is correct. Now I've already run this attack just to save me copying text back and forth. But if I do this with the best rotors, that's not the right spelling at all. So what I'm doing now is it's ciphertext I'm supposed to be. No, it's not. It's plain text. I'm talking nonsense. Of course, normally you wouldn't know the plain text, but this is just illustrative, right? I'm not a real cryptographer. So we're going to calculate the difference between the plain text and our theoretical best current decryption based on rotors. I think it was 3, 1, 4 in the correct place and with the correct starting position, but the ring settings are wrong and there's still a plug board in play. So it's not going to be great, but it's going to be better. There we go, right? So these are the positions where we're seeing some words. Now, actually, if you look at the plain text down here, you can't read that because there's too much noise. When I use the actual known plain text to get all the nice letters out for you, you can see that this has like that's the word cipher probably, right? But you were never going to be able to do that by eye. I mean, maybe if you worked in Hut 6 or whatever, right? They got pretty good at this. So that's not too bad. We've got 200 out of 700 characters, but I would argue it's not enough to really be able to read what's going on. But our index of coincidence was better, and that's why we picked those ones. That's the idea. So let's run the ring settings. That did not take long. And now we've got the word enig at the beginning of our text. That's now if we're talking. So if I look at comparison about this, actually, it's not much better as it happens on this particular, because I picked a terrible contrived example. But if you go for best rings, you can see you've got the word enig. The number of characters is almost exactly the same, but theoretically this has the best bigram score of all of the different ring settings for those two rotors when we fixed the ring ordering. Right, that's the idea. So we've split our key into sections and we're slowly moving towards the result. So if we go back to this slide, we've done step 1, we've done step 2, and now we have to do step 3. That's the last one. Did I say anything about that? No, I didn't. That's the end of the slideshow. So let's do it. The plug board, you can't, there's 110 trillion combinations. My laptop's not that good, so I can't brute force it. But you can do hill climbing. So you may have used a hill climbing algorithm before, but a hill climbing algorithm is basically where you work under the assumption that any plugs is better than none, 2 plugs is better than 1, 3 plugs is better than 2. So you go through all the possible plugs and you pick the one with the best score, the best fitness, the one that improves the fitness the most off what we had so far. Then you fix that plug and you do the same thing again. You get the next best plug, and then the next best plug, and the next best plug. And this is another weakness of Enigma, the fact that it gets continually better as you add more plugs, rather than a modern cipher where if you had one plug wrong, nothing would work, which is what's supposed to happen. I mean, so we do a hill climb. This is fairly straightforward. There's about 325 possible plugs, and then there's slightly fewer plugs once you've fixed one of them, and so on. So somewhere in here, I've got my Enigma analysis, and I have a find a plug. So it just goes through all the possible unplugged characters, all the possible plugs, again, calculates the fitness and returns the optimal plug. And then all we do is we loop for the maximum amount of plugs, right? This was the easiest bit of the code. And then we try it out. So let's run that. Now I'm cheating by only using 5 plugs. If you use 10 plugs, we can talk a bit about what will happen, but basically it just becomes a bit hard. It becomes a lot harder, right? Because fewer of your characters are correct when you get your approximate decryption, which means your fitness function is worse. You may still see a slight improvement, which means that you may still get the right rotor configurations, but it becomes less and less likely, to the point where if you have 13 plugs or 10 plugs, you're going to need somewhere around 1,500 to 2,000 characters of text before your fitness function might start to bleed enough information to actually see it. Now, these are only, I think, 600 characters, this message, so I'm only using 5 plugs. You might get it, but you might not. And that's no fun, right, if we don't get it. So let's run the plug board, which is this button here. And the best plug board was TVAFRWKOBL. And this was my plain text out. So if I copy that into a thing here, if you have a look at it, I mean, there's some words in here, right, ated, subdated, updated, upated. I don't know, it didn't make sense, right? Key, list, you know, there's words coming out. This is not perfect because you've still got the ring positions and the turnover incorrect. You'll see that in a moment when I show you the diff. So letters are like that. I mean, clearly that is actual plain text that's coming out. The thing about Enigma is it's jumbled it up enough that if you see words, it's very likely to be correct. Right, at this point, we're pretty confident about the rotors and the plug board. So let's look at my diff. Where's my, no, it's not that one again. I keep, so if I change it to best plugs, this is the final output. This is literally a comparison between the plain text and this string I just showed you. And you can see it's much better. There we go, right? And that, I'm afraid to say, is as good as I can break Enigma. Right? I can't break those 2 bits without brute forcing the rings and the rotors together, because when you fix the rotors at 0, you don't get the optimal ring positions, which means you don't get the optimal ring settings when you go back to do them later. Right? But you can see electromechanically rotate. I got this off the page for Wikipedia page for Enigma machine. So this is how an Enigma machine works. Something like that. Now, if you were doing this seriously, suppose there was £1 million on the line and you wanted to try and break this, what you would do is you would then put those plugs back in at the top and run this whole attack again with the plugs in place. right? And you'd go back and forth, you'd try different combinations, you'd maybe use your laptop to actually brute force the rings and the positions together and things like this. If you fix the rotors, you haven't got that 60-fold increase in computation time, you can do this. So I could do better than this if I really wanted to, but of course I have the plain text, so I'm not going to. You get the idea. And the last thing I would say is that you don't have to do it single threaded, right? So what I did was, after my video, so I did the video online with an attack a bit like this, and then I thought, well, I haven't really made any effort to make this. I've made this Java fast in the sense that I've made it array indexing and I've not used strings, but it's not fast in the sense that it's single threaded. My laptop has 4 cores and hyper threading and all this stuff. So let's do that. And this Java and modern languages make this very, very straightforward. So if I close this, exit, and I go into here again, so I quit this. Let me know if the text is too small. Although actually I'm only running Git, so it's not I put this on GitHub, so feel free to have a go. Apparently it's up to date. That's good. So what should happen now if I load up IntelliJ again? Very kind of IntelliJ to give all academics a free license. It's very useful to me. But they'll get there, I'm teaching the students Java, so I guess it works for them right in the long run. I probably didn't need to close this because I'm pretty sure IntelliJ could have coped with that, but all this modern technology. Okay, so this should be the same as it was before, except that now in my Enigma analysis, what I've done is I've used a parallel stream. Right, that's the only difference. Right, I literally Googled multi-threading lazy man option in Java. No threads, no starting a thread, checking locks and things like this. So I pre-compute all the lists of different rotors using this function, and then I use a parallel stream for each and run each rotor this way, and then I stick it into this key set, which I made synchronized, but and what a parallel stream will do is look at how many cores you have and just start you up a bunch of threads, and off it goes, right? And it is a lot faster. So let's run it. This is the exact same attack as it was a minute ago, but now it's going to be doing it something like 8 threads at a time, I think. And it just starts, there we go, it's just blapping through them nice and quick. So this took something like 40 seconds before, and it's nearly finished already. There we go, 12 seconds. Right, on my, this isn't my laptop actually, this is my desktop. But we can do a bit better because I happen to work for a university that spent too much money on servers. So if I bring up this is my, not that one. Every time I'm going to bring up the wrong command prompt. It's because they look exactly the same. Right, so I'm on a login node for our GPU cluster. Now this has a lot of people doing machine learning on it. And most of the machines are for, most of the machines have 8 GPUs in, usually expensive ones. We bought them over a period of about 5 years. And what students do is suppose they want to train some sort of deep network. They can come in here and they can use Slurm, which is a scheduling software, to submit jobs, right? If you're an academic, you just submit whatever the hell you like, right? And have a bit of a laugh with it. So we happen to have 2 nodes for our dual CPU Intel AMD Epics with 6400 cores. I can't remember exactly how many cores, lots of cores, right? So let's see how long it takes. So I've git cloned, and I had to ask someone how I ran this on Slurm because I've literally forgotten, but it's something like that. So I srun is Slurm run, 64 CPUs, please, 10 gig of memory. I don't need 10 gig of memory, but it seemed rude not to ask. On the CPU partition, and then I'm going to run this Java, right? And so this is literally going to start it up. What actually happens is it copies the files over to the node, which in this case will probably be Wanda, which is our CPU server. Unless someone's already on it, in which case it's going to sit in the queue and we're all going to be very depressed. But it will run, right? And then it will feed back the terminal, and it does not take very long. It's done. 1.8 seconds. So actually, and so what I might do, I won't do it. I didn't do it today. I might try and brute force the ring settings as well, right? So the ring settings are 26 by 26. So that's 676 times longer. 676 times 1.8 seconds is still not very long. It's about 20 minutes, right? 20 minutes. So I could simultaneously get the correct rotors and the correct positions and the correct rings, and I might be able to fix some of those little bits of missing plain text. I won't, I'll leave that for further homework another day, but you get the idea. Of course, it only takes 1.8 seconds on the server. What I would say though, I'm quite jealous, those M1 Max that everyone's doing around, they are unbelievably quick at this. No one's buying M1 Max for breaking Enigma, but if they were, they're a lot faster than my Intel i7s, I can tell you. So yeah, because I have a friend that kept smugly sending me screenshots of how quickly it was compared to my laptop. So yeah, but that's basically a how to crack Enigma in 2021. I got this from a paper from about 1995 where he did this, but he did it slightly slower than me. But it was the same kind of principle. Only used index of coincidence, did this hill climbing and split it up. There haven't been many attacks since then. There've been a couple of other papers, and really all they've done is messed around with different fitness functions and stuff like this. No one's really doing anything more on it mostly because they've probably got jobs to do, right? And no one's going to pay, right? If people want to pay me to do this, I'll definitely do it. But so I would say it's unlikely that in the short term we're going to see any more significant breaks than this on Enigma. Also, I mean, it's just got a big key space. It is what it is. From a modern cryptography point of view, this is fun. This is catastrophically broken, right? You don't. The fact that I didn't get all the plain text to a modern cryptographer is of no consequence. I got enough plain text, but it's a serious problem if that was your personal details, right? You can guess what the other words would be. You could Google for what the string was. You could optimize this process and get a little bit better next time. You know what I mean? So modern encryption has to not give a single character, right? As opposed to only 80%. So, this is not good enough. It's also incredibly slow compared. I mean, it's streaming Netflix over this, as we were talking about earlier, might be a little bit of a problem, although it would be fun to try. But if you have a very, very short message where your fitness function is not useful because it has to build up a picture of letter frequencies and frequencies of bigrams and trigrams, then this isn't going to work. So the Germans during the war sent messages of maybe 250 characters max, and that was specifically to avoid index of coincidence attacks. And so, they were wise to this, and it is still a problem. This attack works to an extent because this is the length of the message that I'm putting in. If I increase the number of plugs, I'm going to have to increase the length of the message, or I just might not get it all the time, depending on what the plugs are, depending on what the ciphertext is and the plain text is. So it's hit and miss. So I suppose I went into this, a few months ago when I coded this up, I was kind of secretly hoping to completely break it, right? That would have made for a cool video. But I didn't actually, because it's not quite that bad. It's still pretty good. If I sent you a 20 character message in Enigma, I don't think anyone would ever break it, because you're just going to have to brute force through everything and read all the messages to work out which one the real words are. And there's going to be some that look like real words. Yeah. So it's not as bad as people think, but it's also not very good, right? I guess it's not for production code, So yeah, I mean, happy to answer any questions or chat about it.
That was really good. That was awesome. And obviously, I mean, I saw the video, and you've taken it on another level after that. So a round of applause for that. It was awesome. I mean, I've got all the questions, so I don't want to monopolize it. But is Is there a possibility of adding like a machine learning or language analysis on top of that you mentioned there, that you'd have to, on a 20 character one, you'd have to like use a human to recognize the words?
Yeah.
You could use machine learning.
Actually, that's not a bad idea. Like, so I think that when people think that you could use deep learning or machine learning, they think that what you would do is you would train it on a lot of decryptions and it would learn just to do the decryption, right? Yeah. There's no way, because it's just noise. You can't learn noise. But having a machine, having an AI that looks at a sentence and says, is that a plausible sentence? Yeah, absolutely. And it may be quite a lot more robust for short lengths. In fact, I might look into that. I probably won't train it myself. That seems like quite a lot of work of getting a load of text. But yeah, I think it would be, I think there's a possibility. Certainly what it would do is it would give you another fitness function in your arsenal. So I found that if you put IOC in all of the positions, so you do the rotors and the rings and the plug with IOC, it doesn't perform as well as if, for example, you use quadrams in the plug search. But if you use quadrams in the rotor search, it doesn't work, because as we mentioned, the plugs mess up enough of the characters. So a lot of this seems to be which fitness functions you use at what stage, and are getting a bit lucky. And so the more fitness functions you have, the more you can try these things out, the better your luck is going to be. And all you have to do, I think, is to get enough of the plain text that you realize, okay, those are definitely the right rotors. And then you can zero in and get all the other settings. It's when you're trying to jointly solve and you just get nonsense. What tends to happen is if it fails, what tends to happen is that the best rotor position is not correct, right? So suppose your rotors were 215, it doesn't find 215, and then you're onto a bit of a loser, right? It's not going to work. Often you'll find that 215 will be somewhere in the top 10, but that would be, more resources required to find it.
I don't know whether my mic's working. Yeah, it is.
Yeah.
That's very interesting. Very. It does make you admire the people at Bletchley Park and what they had to do, and also whether they had to work out whether that message was a weather report or was in fact a sighting instruction or an attack command or whatever. Because so that they actually were able to optimize what they then put through the bomb, because that must have been. I think it took, was it 26 hours to compute a message?
It's mind-boggling. It's mind-boggling what they did. Like it makes
German.
They had. So all the bomb did was find the rotors and I think their positions, right, under some ring assumptions, and I think it found one plug at the same time simultaneously because of some mechanism that I don't quite understand. That is not enough to decrypt a proper Enigma message. And so they had to do a lot of work beforehand to try and make sure that their menus didn't have a lot of full stops. And they had to do a lot of work afterwards because they only had half the key and they had to try and figure it out. And as far as I can tell, and I imagine talking to the people at Bletchley is the best place to find out about this, but it seems to me that what they had to do was essentially had to look at a lot of text like I was just showing you, and then immediately zero in on the bit that was actually working. There was no, that they would get really good at that. They'd go, okay, I can see from this text, there's no A's in this text. So I think this person has just pressed A, right? This kind of
if we can believe the film, did not somebody come up with the idea of, don't they end all the messages with Heil Hitler?
So we were talking about this before we started, and a lot of the breaks were only possible because of laziness from the Germans in terms of encrypting only A's, or sending a message both for using Enigma and another cipher which they'd already broken, and then they had a known plain text. Right? Yeah. A guy sending a weather report every day, nothing to report, or putting a mine in the North Sea and waiting for them to say there's a mine in the North Sea as a message, working out where this plain text could go was a mission on itself. Yes, you've got this reciprocity thing where that it can't be here because a W would have encrypted to a W and what have you. But so there's a few places it could go. But like you say, you've got to work out that that's even a weather message at all. I think they had a lot of psychological and other know-how, and they knew the operators almost personally. They knew who their wives were, and they knew that they were talking to this person. They often sent this kind of message and things.
Yeah, it's getting the pattern, isn't it?
Yeah, really
getting into their heads.
Would there been? I mean, when you ask a human to make random numbers, we don't make random numbers. In fact, we're awful at making random numbers. So picking random rotor positions, and obviously that would have been a set of people, a small set of people would have decided what the rotor positions were for that particular day. And in fact, there was a sheet. There was a sheet of rotor positions, wasn't there?
Yeah, and actually, there was an interesting thing about this was because what they didn't do is encrypt the entire message with the daily key, because if they did that, then you would have this index of coincidence problem where, yes, each message is less than 250 characters, but there's lots of messages and you can append them all together and get a huge corpus of text. So what they did was they had a message key that was random. They encrypted the message key at the start with the daily key, sent it, and then sent the message. The problem was that they didn't bother to pick a very good key. Right. So, for example, let's suppose the daily key was like ABC. They put ABC in and encrypt something very, very similar to it and just move the rotors 1 or 2 positions because they were lazy or something. You know what I mean? And so you could often have a go at guessing positions quickly by just assuming they took the path of least resistance in setting up the machine, which would, again, require a massive amount of knowledge and understanding of the psychology behind the people just sitting there doing this every day. Yes, I mean, Louise is absolutely right.
Yeah, don't believe the film.
My problem with the film is I have a great respect for Benedict Cumberbatch, but he only has one character that he plays, which is a kind of annoying smart guy. That was essentially what the film was, and I enjoyed it a lot. But yes, it's not true at all. He worked very closely with all the people, Bletchley Park, and they were all really, really good at it as well. And it's not the Turing bomb, is it? It's a Turing-Welchman bomb. So yes, I know what Hollywood were doing, and I suppose it's good that they drew attention to the story, but they could have just made it a little bit different.
Yeah. It's only called the bomb because the Polish solved a great swathe of it before even Turing and Welchman.
Yeah, I mean, we would have been nowhere without the Polish either, right? They worked out the wirings for a lot of the rotors that we didn't have, and they also had mechanisms to decrypt messages based on the fact that the key was often used to be sent twice. So suppose your key was ABC and your daily key was some other thing, you'd go ABC, ABC and send that off, and then you send the message. The fact that it was sent twice meant that you could discount certain configurations and things. Again, kind of in the same way that the bomb would.
And didn't they also know, though, the people they knew before the war, the people who were most likely working on the project, and they weren't all German mathematicians. There were, people from the Axis powers as well. But I mean, a lot of high-level mathematics was being done in the late 1800s, early 1900s by Russians, and like Markov chains, and how do you come up with that one?
I get the impression, so I don't know all the history of it, but I get the impression that the Germans, most of the Germans thought that Enigma was unbreakable, but there were some Germans like the Navy who were pretty sure it was breakable, and they knew mathematically that there were these weaknesses, and they weren't stupid at all. And that's why they added the fourth rotor with the extra.
Yeah, there were two different models, wasn't there? The one they had on the U-boats was only, was it 4 rotors?
4 rotors out of 8 different possible rotors, and it used to be 3 out of 5, and then it was 3 out of 8. So yeah, the Navy insisted on 4 rotor machines. Now actually, the Turing bomb worked just as well with 4 rotors. You just had to build a special bomb with 4 in a row instead of 3, and you could try fewer combinations out. But there were the Americans. That was when the Americans were in the war, and they had huge resources, and they just were building bombs all over the place. Basically, we didn't have that many, I don't think. So we used to actually send our naval messages off to them to solve for us.
Yes,
because, we designed the thing, we ain't got the money to build it. So
I think on the Americans, what I find amusing is the use of the word computers was basically a lot of women working on the atom bomb. Which was right. They were all known as computers because they were computing, and probably that famous woman who did all the calculations for the Apollo program. So
yes, that's going to annoy me now.
Yeah.
Please someone chip in and put me out.
We should know these people's names, shouldn't we?
I know, I should know who these people are. Yeah.
Yeah. So it's all done by hand. What I noticed when you were doing those, when you did those, the cuts, and you know, with if you laid one over the other, because I started working out and saying, well, that's success. That is something up, you know, key pressed, update, up, whatever. So when you start overlaying those sort of things, you start to see a pattern, which is something that humans are very, very good at. I mean, the typical one is where somebody does a sentence and then changes the letters in each word, but the first and last letter is always the same. And we're very good at actually recognizing what that word is. And I suppose one of the things that amazes me about Google is the fact that you can spell things really badly and it can still work, it can still give it you. But that's based upon they've looked at the end results of things to be able to work out what most likely it is. So it's awesome. Awesome.
Yeah, good to meet you, Louise. Louise is heading off. Yes, it's quite interesting. And I think the other thing is, so I didn't talk much about my known plain text fitness because it seemed a bit like cheating, right? But actually what you could do once you had half of the message or some guess of where some words are, is you could put the known plain text in, and then your scoring function becomes much less noisy, because essentially it never incorrectly gets anything, right? Either your text is correct or it's not, and then it will work with many more plugs. So if you want to break a 10 plug Enigma, having some idea of some of the words in the right position is really going to help. But I haven't explored that too much. I mean, I might mess around with it at some point, again, in front of a TV. But, you know, I've got this code now, so I can sort of try things out and see what works and what doesn't. But my general experience was that if you start to push a number of plugs or you shorten the message, it becomes a lot more difficult. I mean, maybe obviously, but it's not trivial.
Do you think there are other computer languages, maybe, or other constructs that might be better at it than Java even? I've got no idea about the answer to that question. I'm just interested to think there might be more mathematical languages out there.
Yeah. I mean, I don't doubt there are probably fitness functions that are better that I haven't considered. Right? These are the ones that everyone talks about when they talk about breaking Enigma or anything like this. And short of the obvious one, which is just whether or not there's more ease. You know, the standard single character letter frequencies. But no, I mean, the reason I used Java was because I was programming up most of these algorithms in Java anyway for my cryptography module. I haven't decided whether they're going to be formative labs or assessed coursework yet, but we'll see. But in Python, it works fine. There's a lot of Py implementations. It's a bit slow. So, I had speed in my mind, and I don't tend to use C or C++ because it's been a while. Right, and I don't want to spend other time messing around with pointers. So I didn't explore any other languages. I don't know. I think that anything that could do a better job of working out whether you've got plausible text, that's really where the winning strategy is going to be.
We're also talking about using computer cores, but we know that obviously mining Bitcoin and things works really well on GPUs rather than CPUs. Would that help in any way?
Yeah, I mean, it would. Yes. So. Actually, the problem here is that my code is not very good, and so I've got this parallel stream running on 60 different combinations of rotors, but each thread then has to still do the 26 by 26 by 26 by 26, loops. So what you would have to do is find a way to partition the thing even more granularly than that, and then you could put it onto hundreds and hundreds of cores. I think that an individual CUDA core on a graphics card would have enough memory to do one of these. Because the problem you have with GPUs is that each core is pretty primitive and they don't have much memory. And if you start having to do talking to shared memory, then it becomes much slower. But yes, I would imagine this would be substantially faster. I mean, maybe something to look into. I mean, I don't want to spend too long doing it. I do have this big server I can use instead. But yeah, I mean, hypothetically, right, you just think about what your search space is. If you could introduce if you have your rotors and your start positions, that's 1 million. And then you introduce the 2 sets of rings. So that's another 600 times slower. One plug that's 300 times slower again. But if your thing is only taking 20 minutes, or if it's only taking 2 seconds normally, multiplying it by 600 and then by another 300, it's slow, but we're talking days and weeks. It's theoretically doable. Of course, in the war, it was useless, right? They had to break it in a day, otherwise everyone had moved on. So, this isn't going to work for that either. I wouldn't have got a job at Bletchley Park. They might have hired me just for access to my laptop.
Yeah, and your time traveling self.
Yeah.
Well, if you ever get the chance, listen to Hot 33, which is a comedy on Radio 4. So it's nothing about encryption. It's just comedy, but
Okay.
they're based in the hut in Bletchley Park. But it is quite amusing. The characters.
And then one last one, just to take that one step further. Obviously, we're using quantum computing now to help break and encode stuff, I guess. Again, that just takes that up to another level, that using qubits and things like that, we can.
Yeah, I mean, so I don't know enough about quantum to know exactly how it could be applied to Enigma, but and one thing to remember about quantum is it isn't just going to run your Java faster, right? There's specific algorithms and things that it runs. But Grover's algorithm is a way of reducing key search space. And so theoretically, it would get quite a lot faster.
Yeah, but aren't there only 2 of them in the world at the moment?
Yeah, I mean, yes, this is a hypothetical. So I remain, personally speaking, I remain unconvinced that quantum computers are anywhere near. And I don't mean like in the next 20 years. I mean, maybe I may never see any, like of note, right? Yes, they exist, super cool with 5 qubits. But, there's talk of them breaking RSA. Well, they've got to get a lot more qubits before they can do that. So I think it's wise for people to be thinking about how to stop them from breaking all the encryption. I get that, but I don't spend a lot of my time worrying about it. So yeah, I think because there's a problem with scale. I think these qubits are very noisy. So as far as I understand, what you do is you do an experiment, and you have a certain probability of it going one way or the other. So you have to run the experiment a number of times to work out what the actual answer was out of those 2. And the problem is that when you make the thing bigger and bigger and bigger, this noise becomes more and more pronounced. And you've got to run everything again and again to try and work out what's going on. And I don't think it's been proved that when you scale to the sort of sizes we're talking about, you can ever get above the noise. That remains to be seen. So we will see. But like fusion, it's just on the edge for the last 50 years, and they're just there, and then suddenly, it's another 25.
Yeah, but aren't they going to build a fusion reactor?
China.
Yeah, but it's not going to be. They're building ITER in France. I mean, I only know about this because I got on one of those YouTube rabbit holes of watching about fusion a few days ago because it was interesting. They're building ITER in France, but it's research based, so it's not going to generate power. And they're building one. Jeff Bezos is helping.
So don't rely upon having your house.
No, they've solved a lot of problems with fusion, but we're talking about a plasma at 100 million degrees in a donut, and it turns out that's not that easy. And so. Yeah, I mean, my physics is not strong enough to know, what they need to do. But at the moment, I think they're hoping that ITER in its lifetime will produce at least once will produce more energy than it takes, and then it's about sustaining it for some amount of time.
I think really we're waiting for somebody to come up with Asimov's positronic brain. She's a completely different type of organic, more slightly, or artificial organic type of neural networking.
Yeah,
but we're it's fantasy at the moment, isn't it?
Yeah, it is, and a bit like quantum and a bit like fusion, this sort of artificial general intelligence gets bandied around as something that we should all be very worried about. I don't spend much of my time worrying about it. I train deep networks for a living, and none of them are very smart. So, I mean, famous last words, But I think
artificial intelligence is an illusion. I'm reading the Kate Crawford's book at the moment, which is the Atlas of AI, and she's a researcher who's been works for Microsoft Research, which is a separate section of Microsoft. They're not influenced; they sort of report and comment in, and it's interesting. Some of the things. One of the things just got me going is lithium ion and lithium ion batteries. Not all cars have got the same lithium ion batteries in them. There are 3 types, and the ones used in Teslas are not recyclable because the lithium is they're like A2 batteries, and it's because they're coiled. It's very difficult to actually retrieve the lithium from them. Whereas the other ones, the one that's in Nissan, are flat packs, and they're a bit more easy to recycle. It's little inconsistencies that everybody putting in their ore on these things, but it's interesting about how the number of human resources, the amount of stuff we're putting into all this. I mean, how much power does the data center run? How much power does the mining Bitcoin? They're talking about the carbon footprint on it. It's huge. But I think one of the nice things about the machine doing machine learning is that you create a model that you can, so you're processing something that you can then use.
The hope, yeah. Yes, we use quite a lot of electricity to train our models, and it is something we know. We're not oblivious to it. We're not trying to bury our heads in the sand about it. I mean, compared to Bitcoin, it's tiny, right? But it is still 60, 70 GPUs, 200 watts each, running most of the time, and all the associated CPUs and stuff. I mean, I've been in the room and it's hot. Maybe we can get some kind of solar panels on the roof, or invest in trees or something. I don't know. I mean, short term, I don't think we've got a very good solution to it. Deep learning and AI in general is very computationally demanding, and it's something we have to think about. I think the biggest thing to think about is Bitcoin and trying to sort that out, because you can't justify that kind of power usage. I can't think of an argument for it. I've never seen an argument that's coherent for it. I can understand that people might be interested in the cryptocurrency for whatever reason, but the environmental cost is massive and it needs sorting out. And so, the sooner they do that, the better. Because like you say, it's not doing anything, right? It's just people like Musk throwing money around the place to different people, and money moves back and forth. They haven't produced a machine learning model. And, as far as I know, we're not all running on smart contracts yet and things like this. So, I want to see a few results if we're going to use that much electricity for it.
Yeah, I think a lot of effort needs to go into more about how you pull your training data together, because that's one of the biggest challenges I've got, is actually getting data into a machine learnable format that you can actually process. Just from from the language point of view, and from all the data sets that we actually have, and it seems like the effort is going in the sometimes you feel like it's going down the wrong thing,
data set curation is a huge problem, and it's a problem where I work as well, because I work a lot with biologists and medics and stuff on medical imaging, biological imaging, and their data sets are always an absolute catastrophe, right? And it's because they've just got better things to do than to worry about curation of data. So they'll give you an Excel file where one of the fields is the color of the text, and you've got to turn that into a machine. You've got a machine learn. Like it's not easy. And you get better at it, but it wastes a huge amount of time. And the other thing is that none of the biologists send data to other biologists, because then they might steal their work, right? They're very protected.
Yeah, well, that's the problem with the research environment, isn't it? Everybody says, oh, well, they're all talking to each other. They say, yeah, they're talking to each other very candidly, though, in terms, they've got the barriers up because they're absolutely, paranoid about it. When they get to the end, they don't want to have somebody say, yeah, but somebody's already done that. Taking those ideas. You're absolutely right. But it's the commercial use of it. So, because at the moment, if you look at Chatbox and where that's going, it's all about sales or large companies having some sort of interaction with their customers. And I'm looking at it and going, oh, well, what about just finding information about stuff that we've already got? Like, how do I repair this? Is this all right? Those sort of questions. And it seems to like that's just not interesting to people at one level. Yet it is actually really going to be beneficial. Because we're getting so much. There's so much stuff we could do stuff with, but there's not enough people who are interested in actually. It's like it's not exciting enough. It's like in the BIM world, that's building information modeling. 3D is the sexy stuff, but the data underneath it is the important stuff. But nobody's, people are worried about the clash detection and the 3D and the visualization, because that's the sexy stuff. That's the thing that gets people excited, rather than the stuff that tells you this system is going to fail in 32 hours because blah, 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 So anyway.
In machine learning, the problem is that, you've got these big tech companies with massive resources training these models that are the ones that perform really well on image classification or segmentation tasks. But none of these models are actually going to be used by anyone because they're much too big. So the reason that the standard, so I work a lot in segmentation, which is labeling pixels and images, and there are lots and lots of modern techniques that you just can't really train because they take up too much memory. And I haven't got 8 GPUs to spare for one task. So I use a smaller one and it works fine. And I think that there's a push in deep learning and machine learning in general for bigger and bigger models because of the performance benefits they give, with no consideration for the practical applications of them at all. Right? No biologist or medic is installing 8 GPUs in a server so that they can classify their images. And so it slows progress, I think, and that is a huge problem. I don't know what the solution is. Eventually, people will probably tire of doing the same stuff, and maybe they'll try and make the problems a little bit more efficient or more interesting then, I guess. But it's taking a while.
I'm conscious it's 8:30, so I'm not sure how long you want to stick around, Mike. But I don't know if anybody else has got any questions that they want to ask or points they want to make. Or
yeah, I probably shouldn't stay too long just because I've got probably kids wandering around somewhere that I need to do something with. Shepherd around between rooms. But happy to answer any other questions. Do have a go with the Enigma code, by the way, if you fancy a bit of Java. As far as I can tell, it compiles and runs.
Works on my machine.
Don't judge me too harshly. I don't actually work in industry, so I don't really know how to write proper code.
Is there anything from what you've done there that is translatable to modern cryptography?
I think the best thing about Enigma is it gives you an understanding of what it is that was needed and what modern cryptography does that this doesn't do, right? So the first thing is that you don't get a one-to-one mapping from character to character, because if you did that, you've just got to work out what that mapping is, and it's much easier. So in AES, for example, which is the encryption we're using right now, almost certainly you've got 128 bits that get mapped to 128 bits, and if you change a single bit, everything will change, basically 50% at random. And so working out a function of how that went to that is almost impossible, with our computing power. So you're left brute forcing. The other problem is that you can't, if you're splitting the key space problem, there is no part of a modern cipher that doesn't really have an effect or can be kind of skipped. And so I could only do this because I could ignore the plug board essentially, and it kind of worked anyway, and then sort the plug board out later. In AES, there's no part of that you can do that, or char any modern cipher. So I think if I was teaching this to students, what I would do is I would pitch Enigma and talk about the weaknesses such that those are the things we're going to address, right? Which is what modern cryptography is about. The other thing that's changed in modern cryptography is the methods and the way the scientific nature of the field is totally different. So in the 40s and the 30s, someone came up with an Enigma machine. Yes, they were very advanced mathematicians breaking it, but no one had written a formal proof on the security around Enigma. No one had done a formal analysis of it. So when the Germans bought Enigma machines from the commercial company that was making them, they didn't come with a mathematical proof of security or anything like this. It was just kind of implied by the fact that you've got a lot of rotors and they can go in a lot of different places. You don't get away with that now, right? You can't publish an algorithm and say, well, it's pretty secure because look how many rotations it has in it. You have to say, okay, mathematically, it's at least as secure as this, which we know is going to take this long to break, and so on and so forth. It's all about security margins, essentially. So modern cryptography is much more scientific in the way that you go about finding what works and what doesn't. And just guessing and intuiting your way towards a solution like this is, or like we did in Bletchley, doesn't happen anymore. Like, I mean, you know what I mean, to most extents anyway. And I think that's interesting. In a way, I think the historic stuff is more exciting because of that, right? This guesswork, it's like a detective puzzle. You don't have so much detective puzzles now. There are known mathematical techniques for trying to break algorithms, and you just try them out as if they work. But
So are you saying that when somebody does create a new encryption, that there isn't another team that tries to break it before they sort of?
There absolutely is. I mean, the best example is the Advanced Encryption Standard, or AES.
Yeah.
Was part of a competition with 15 other entries. So it was one algorithm among 15, and they had rounds of voting. And between those rounds, 1 or 2 years passed in which papers were released attacking them and examining how fast they were to implement on hardware and smart cards and chip and pin and tiny embedded devices. How fast can it run on Arduino, right? Because it's not always going to be a supercomputer running these things, because there are some algorithms that are just as secure as AES, but they're slower, and so there's no reason to use them. So yeah, this kind of black box, we won't tell you what the wiring is, you don't need to know, that doesn't happen anymore. I mean, the best example is Caesar cipher, right? If you didn't, I mean, I think the joke is that Caesar didn't need to worry about his encryption because no one could read anyway, right? So the people transmitting his messages didn't know what it meant. But the thing about Caesar cipher is it looks kind of like gibberish, but if you tell someone that it's just been shifted, it's going to take them all of 5 minutes to work out what it is.
Yeah.
It doesn't hold up once you know how it works.
Yeah.
And that is very much the basis of modern cryptography, is everything about how it works, and
that's the sort of the story of the Americans used Navajo Indians when they were fighting the Japanese when in the confrontation with the Japanese, because the Japanese just couldn't work out, didn't know it was Navajo that was being taught over the radio. So, but once you do know it, that's the end, isn't it?
Yeah.
I mean, when that competition was happening, and they're looking at the new cipher to replace DS. I remember when Ringedel was first announced, etc. God, so long ago now, 2000, early 2000, 2001. And AES came along and published it. One of the key things is it had to be completely open and published so people could see how it worked. And as you say, you can see exactly how it works. Go on, have a go now, try and break it. And immediately they went into the next round of working out what's going to replace AES. And actually what's happened is nothing, because they've required nothing more powerful. And in fact, the only threat that's been against the chosen AES is because of compute power and being able to actually do the same job but actually use less power. And there have been a few ciphers that have come along that are actually able to be run on lower processors. Yeah. But still, most people just go, oh, we'll just take the hit, we'll just do AES. Which is interesting.
I think so. There's Char, that's one.
Yeah, but that's not. It's a different type of cipher, isn't it? That's streaming rather than block based. But yeah, that's very, very efficient. And I think it's in a couple of processors now as well. So you don't even have to waste main horsepower to drive it, because it's in your coprocessor.
Efficiency is a huge thing, right? Because there was an algorithm called Serpent that was one of the finalists in the. And as I understand it from reading around in various books, it's much more secure than AES in some sense, right? It's because basically, it's like AES, but with double the number of rounds and doubling out of everything. But it's also slower, or at least a little bit slower. And AES is secure enough. And when you're doing a chip and pin transaction, it's got to be quick. So, and if you're Amazon, I mean, not if you're Amazon, maybe because they've got enough servers, but you're hosting some sort of cloud service. That's a lot of encryption you're doing per second on everyone's data, everyone's communication. Adding a 10% overhead or a 10% efficiency saving is a really big deal on these algorithms, which I think is really interesting. So Ian has put in the chat about this thing. I will read this. This is interesting. Okay, yeah, nice. There's a lot of mobile phones and all this kind of mobile stuff. They've always used historically very bad ciphers. It's always quite fun. A design backdoor. I always do enjoy a good designed backdoor. That doesn't surprise me. There's in my experience, to me, because there's a lot of stuff in the news about how we shouldn't be allowed end-to-end encryption and stuff. Right? I'm not convinced that the agencies really care, because they're busy just hacking all of everyone's mobile phones and stuff like that. Right? Attack the end device. It's much easier. Part of it is, I think, is a look over there. We're breaking the encryption, and then
Did you see what they did recently to break a massive load of cyber criminals?
Yes, I mean, it was fabulous. So
they
actually,
gave them the program, didn't they?
Yes, yeah, they created a new secret chat program that was better and more secure than Telegram, etc. They said, and got all the criminals to be using it, and then we're just basically reading all the messages.
The best thing was they charged the criminals to use it per month. I mean, because if you didn't charge them, no one would take it seriously, right? So we're a legit company.
Yeah, absolutely.
And the criminals. So there are things like EncroChat got hacked. And that's in the courts at the moment. There's a lot of that about. These end-to-end encrypted phones are a huge thing for criminals, because they feel like they can then say what they want rather than having to talk in code all the time. But it's a huge risk from a criminal point of view if you don't know the whole chain of what's going on from that device to that device. As it was EncroChat, for example, it's not absolutely clear how that was broken, but they got hold of the servers, and then they could push updates to the phones, and then they could get the phones that way. So there's going to be a lot more of this stuff, I think, because at the end of the day, no one's breaking AES. So, for two mobile phones using Signal protocol or WhatsApp or AES, you've got to get in at the server or on the end device. And so we're going to see a lot more of that, I suspect. I don't think they're going to get anywhere with this argument that all these messages shouldn't be encrypted, because they already are, right? And all it will mean is the rest of us won't have encryption, which seems a bit wrong.
Fair. Cool. Right, I'm going to let you go. And thank you so much for taking the time to take the time to make the original video, and then to expand upon it, and then take the time to deliver it tonight. It was really, really cool. So round of applause for everyone for that. That was really cool.
No, it's no problem. I do like talking about encryption.
Yeah, and good luck.
As you can see, I can talk for quite a long time without stopping. So everyone can have a break.
Is the course that you're doing, is that a module of a larger course, or is it a course?
Cryptography, yes. So I teach computer security at Nottingham, which is a module in the third year. Anna took it, as far as I know. She did well. I'm now introducing another module, cryptography, and what I'm doing is I'm taking the lectures that were on cryptography from security and thinning them out to just the bare essentials, and then people can take this optional extra module if they want to know more. That's the idea. So much more detail on things like elliptic curves and stuff, which we just don't have time to discuss in the regular module. But it's a third year module, so it's technically difficult. Everyone can program already, so we're going to be looking at the maths behind some of these things and looking at it in more detail, but it's still in an applied engineering way, because that interests me much more. Some of these textbooks, it's just all proofs. And so, you can get to the end of the book and you can be very sure that AES is secure, but you're not really sure when you'd use it, because they haven't told you. It's that kind of idea. I much prefer the practical side of things. It's just sort of computer scientist I am, I think.
Very good. Cool. Yeah, well, thanks again. And hopefully when we go back to in person at some point next year, we'll actually have you along for an in-person meetup of some sort, and you can talk cryptography that time rather than Enigma. But that'd be awesome. Yeah, so thanks again, and we'll see you all soon.
Thanks, everyone.
Thank you.
Cheers. Thank you.
Thanks.